Can you see my screen?
Yep, I can see your screen. I think we should wait for a couple of more minutes. Just, people are kind of pouring in.
Yep.
That's okay with you.
Yeah.
Hi, Moshe.
Hello. Hi. But my talk is on Wednesday, right?
Yeah.
Yes, I believe so. Yes.
Yeah. I'm just paranoid with all these time differences.
So am I. I'm like, one of the
give-
keynotes is at 3:30 a.m. today. I don't know how well I can that.
Well, when I give a talk in Australia, it's the time difference is about a week.
Right.
Okay, at least I know that the Zoom link works.
Yeah.
Yeah.
Moshe, according to the program, your session is supposed to be Thursday morning, right? Keynote 3, right?
Yeah,
Yeah.
Thursday morning, which is my 6 p.m. on Wednesday.
Oh, yeah. Okay.
That's why I'm always checking it. That's why I always say, you send me the calendar invitation. Otherwise, who knows?
Yeah.
It's very unsettling.
True.
And I think I did send an email to all the presenters about the program. So hopefully they all turn up. I got some requests that some of them may want to do some recording, but then I swapped their sessions to a different time slot, and it seems that they were happy. So I hope there would be no issues.
You can probably start, I think, Jay.
Okay. All right. Hello, everyone. Welcome to ATVA 2021. I'm the PC co-chair with Vijay Ganesh, and the general co-chairs are Jin Song and Jing. So the ATVA 2021 conference was supposed to be hosted on the Gold Coast in Australia, but unfortunately, due to the COVID-19 pandemic and all the travel restrictions, the program committee then decided to host it completely online. But still, here's a picture of the Gold Coast. If you haven't been here, should pay us a visit sometime. And I'd like to just say the acknowledgement of country as a tradition of events hosted in Australia. So I would like to acknowledge the Aboriginal peoples and Torres Strait Islander peoples as the traditional owners and custodians of the land on which this event is supposed to be taking place. We recognize their connection to land, sea, and community, and we pay our respects to them, their cultures, and to elders past and present, and extend that respect to all Aboriginal and Torres Strait Islander people. And with that, we will start with the ATVA 2021 officially. So to begin with, I'd like to give an overview of the submissions and reviews. So this year we've got 75 submissions, and we had a very competitive selection process. So in the end, we selected 19 regular papers and 4 short papers. So we made sure that most of the papers have at least 3 reviews, and some of them have 4 reviews. So this year we have 61 PC members, and they've contributed a lot to the selection process and also the organization of the conference. So we thank them very much. And we also have some external reviewers who contributed to the reviews. So for the total number of reviews, we had 176 reviews from the PC members and 50 reviews from the external reviewers. So here is the demographics of all the submissions and the accepted papers. And this year, we've got lots and lots of submissions from Europe and also from the United States and UK, and some submissions from Australia and China as well. And these are the majority of places where people submitted the papers. So thank you guys very much for submitting to ATVA 2021. And of course, we also got submissions from other countries. And we'd like to thank our sponsors. So this year, our sponsors include Formal Method Europe, LNCS, Springer, and Griffith University, who provided lots of the facilities for registration and websites, and also of course National University of Singapore, especially Jin Sung's team, who provided lots and lots of help in the organization and all the tech support and the Zoom licenses, etc. So thank you all very much. Last but not least, ATVA 2021 would not have been successful without the contribution and involvement of the program committee members and the external reviewers who contributed to the review process. So as total, we had more than 220 reviews and the selection. So with that, we selected the best contributions. Now, this event would not exist if the authors and contributors did not submit their papers. So we address our thanks to every person, every author and reviewer and program committee member and organizing members involved in the whole process. We also wish to express our special thanks to the general chair, Jin Sung and Jing, and the steering committee members, particularly Jing and Fan and Jie Hong and Yu Fang, for their valuable support along the process. That's a quick overview and opening. So thank you all very much. Now, Vijay, did you want to say something? Or I can give a quick.
Sorry, no, I didn't have anything to add. Thank you, Jay.
Maybe I'll give a quick walkthrough of the program. So we're looking at day 2 right now. So currently this is the opening. And basically each day we would have 2 sessions. One is in the morning of in Australia time, and the other one's in the late afternoon. So our goal is try to make sure more people can be engaged online live. So each session would have 3 talks, and we would have a huge day break. And each day we would have a keynote. So the keynote for the first day is Sir Tony Hoare, but unfortunately, Tony has been ill recently, and he and the other collaborator, which is Bernhard Muller, asked me to give the keynote on his behalf. and he would like to collect some questions and then maybe have some technical discussions with the audience later on through email. And then we have day 2. So the structure, the schedule is quite similar. So day 2, we have the second keynote from Andrew Yao. And that was scheduled in the afternoon in Australia. And day 4 and day 5's keynotes are in the morning. So day 4's keynote is Moshe Vadi, who's here right now. So thank you very much for agreeing to give a keynote. That's fantastic. And yeah, on day 4, so session 6 only have 2 talks. So basically session 6 would start at 4 p.m. in Australia. Day 5 in the morning, we have a keynote from Somesh Jha, and then followed by 2 sessions. And that'd be the last day of the program. So we hope you enjoy all the talks and keynotes. And yeah, that's I think that's all for the opening. Any questions? Right, I think so the format of each talk, the technical talk, would be about 30 minutes. So it's roughly 25 minutes talk and 5 minutes Q&A. And I think at the end of the talk, you're encouraged to open your microphone and talk, or if you don't want to talk, you can text some message in the chat. And yeah, the session chair or the tech support person would read the questions and try to engage everybody to have a live discussion.
Shall we? We could start a bit early if, or do you want to start exactly at 10:30 your time?
Yeah, I don't really mind. I'm wondering, would there be any more audience coming in at 10:30? Could be the case.
Okay. So you could entertain us with some news about Australia, because we don't hear that much over here.
News about Australia, it's not much. I have no idea.
You're not.
Well, Melbourne just out of lockdown, which the city was probably longest lockdown, and
Yeah.
but it's probably still forbidden to travel to Queensland, I guess, unless Queensland is 70% or 80% vaccinated, then inter-travel will be allowed only for vaccinated people, I guess. That's recent news I heard.
I heard in New South Wales, the premier, which is like the equivalent of governor in the US, said that they would open border and allow international travels, and they would basically just get rid of all the quarantine process and hotels. But then later on, Scott Morrison said, border issues is a federal issue, so what you say doesn't matter. So I don't know.
What about Canada? It's like US, pretty freely open, I guess.
Yeah, no, there are no lockdowns here, but you do need to show the COVID that you got the COVID vaccine to enter stores and or go to sit down restaurants and so on.
Right. And you guys can freely travel to US, I guess, right?
I'm not sure about that. I'm not 100% sure about that.
Okay.
I think that's still. I think it's possible for someone to go from Canada to US, but I don't think it's possible to go the other way at this point.
Oh, really?
That's what I think. I'm not 100% sure.
Right.
Moshe, do you have any information on travel restrictions from US to Canada or vice versa?
No, I heard the US was pretty relaxed. I know one of the professional tennis player from Australia. He told us that, he was tested positive,
Mhm.
and then they said, sorry, then you cannot play US Open. They said, okay, what are you going to do? I should be isolating in my hotel for 14 days. And that's usually what Australia going to do. And the US official said, no, you can just, stay as hotel as much as possible. But if you want to go out shopping, get food, that's fine. You can go out. So they don't need to isolate, even with positive case. So I believe travel to US may be easier.
Yeah.
It's going to be. I think the US is opening in November, early November. The US will open more. Will become more flexible.
Right. Cool.
Maybe everybody could introduce themselves or something like that. That would help pass time another 11 minutes. How about we introduce each other? So it's 16 of us.
Okay.
Well, for some reason,
where is
yeah,
everybody? You had 66 papers, 66 PC members, and what do we have? 60 people here. Where is everybody?
I guess.
Probably half of
I
them
think the
in
European
Europe.
probably is sleeping, right? The
Yeah.
European is like midnight. European is sleeping, and the US at night. I guess that's why Mushi is here. I suppose in Singapore, but now I'm in Australia.
how are things in Singapore?
Singapore actually is kind of a half lockdown in a sense. Like they allow people to do some sports. For example, you can play tennis, but only play single. You cannot play doubles because 4 people. The kind of restaurant, you can only have 2 people sit in. You cannot have a big group. But they 80% vaccinated. So, but I heard it's still a lot of restriction. It's daily, maybe around 3,000 cases for small cities. Still a little bit of worry.
Well,
Yeah, you're absolutely right. At daily cases numbers are about 3,000. So most of us work from home.
Right.
well, the holidays.
Yeah, I'm quite lucky in Queensland. Queensland has 0 case, and they try to maintain 0 case. So now everything free. Can do anything you like, but wearing mask still. Indoor. Apart from that, it was really free. But not allowed Sydney or Melbourne people to come in. So only truck drivers are exceptions. Yeah, Australia is still pretty conservative, very careful. But I don't think they can maintain 0 case for too long.
It's impossible to maintain 0 cases. Not
Yeah.
everybody's vaccinated, and the virus will find anyone who is not vaccinated.
Yeah.
How about everybody say their name and affiliation, so that I'm PJ. I'm from University of Waterloo in Canada. Maybe Moshe can go next. On my screen, Moshe is next. So
My name is Moshe Vardi. I'm from home. I've been at home for 1.5 years, so it feels like I'm from home.
exactly.
Hey, hi everyone. My name is John Khan, or you can call me Michael. I'm from NUS, National University of Singapore.
Best food ever.
Oh yeah, yeah. Welcome. Yeah, come.
Yeah, I've been there twice. It's really great. Exactly in the plaza right behind you. I think that's where the
Yeah,
somewhere
yeah.
there.
Yeah, that's the U-Town. Yeah. We are very proud of the Singapore food, all kind of flavor.
Yeah.
Whether you like spicy or non-spicy, whether you prefer Western or Eastern, all kinds of food.
And very cheap too.
Yeah. Very affordable.
Very good. Yeah. In my 2 years of staying in Singapore, I've never cooked once. Nobody cooks in Singapore.
Okay, so we know Jay already introduced himself. Next is Dong.
Yeah,
Dong.
I'm also from AOS, but now I'm in Australia, in Brisbane. Yeah, I'm going back to Singapore probably in a month's time.
Okay. Next on my screen is Rajeshri. He vanished.
Yes, hi. So I'm a PhD student at Max Planck Institute of Software Systems. And so I'm currently in Germany, and I'm working under Daniel Neider. So yes, I'll be giving a talk today about my work. So
What time is it for you?
so it's 3 a.m. for me.
Oh, okay. You can always say, we can say good morning to you.
Yes, I already woke up.
Amazing. Awesome. Next is Gong Dong. Go ahead, please.
Yeah, morning everyone. My name is Guangdong Bai. I'm a senior lecturer in University of Queensland, Australia. So now I'm in my office. Probably I'm the only one who are in the office now.
Awesome.
So I'm gonna chair the first session. I'll see you later.
Next is Eddie. Eddie Muscardin. Go ahead, please.
Hi, I'm Eddie. I'm from Croatia, or more precisely, I'm working in Austria. And yeah, here is also 3:30 a.m. And yeah, I will be holding the next talk. So if I say something stupid or make a blunder, blame it on the time. And
That's a good idea. Next is Ang Peng. Ang Peng, please go ahead. Okay, Emily.
Hey, I am in industry. I'm a software engineer at Google in Sydney. I studied at UQ though. Did some formal method stuff there.
Awesome.
Lovely to meet you all.
Fantastic.
Nice
Next
to
is
meet you.
Jan. Go ahead. Next is Yan Zhao. Yan, go ahead, please. Okay. And then MC Cart JG. Are you
How do
there?
you pronounce it? How do you pronounce it?
Yeah, I know. McCarthy, probably, I think. John
Yeah, it's
McCarthy.
me, McCarthy,
Hello.
Jim McCarthy. I'm at DST in Adelaide, in Edinburgh, and at Edinburgh, Australia. And I'm just a tourist today, so I won't be listening to too much, but I'll be listening to the talk tonight and a bit more tomorrow. So anyway, good to meet everybody.
Thank you. Welcome, everybody. So, yeah, I mean, Angpeng and Yan Zhao, if you're there and can hear us, please do introduce yourselves. Go ahead, Yan.
Nice to meet you. I'm not sure whether I didn't notice it. Yeah, my name is Yan Xiao, and I'm now I'm a research fellow under the supervision of Prof. Dong in NUS, and my research interests are related to the trustworthy evaluation of deep neural networks. Yeah, and previously during the PhD period, and I mainly focus on the bug detection and bug localization. Yeah, thank you.
Fantastic. Angpeng. Okay. So I think we are about a minute away. So maybe Jay, you can perhaps start introducing the speakers maybe and go from there.
All right. So yes, I guess we can start 2 minutes early. That's so good. So the chair for session 1 is Guangdong. And I think Guangdong's here. I've just made him a co-host. Yeah. And in first session, we have 3 talks. I think first speaker is Eddie, who just introduced himself, and he'll be talking about a tool that is an active automata learning library. Well, I guess maybe Guangdong can introduce the others as a chair.
Sure, thanks, Zhe. Morning, everyone, and also good afternoon, good night. I'm so happy to chair the first session of the main conference. And in this session, we're going to have 3 papers. The first one is from Eddie. I think I saw Eddie just now. The time for Eddie is 2:30 a.m. Hi, Eddie. So can I ask you to share your screen, share your slides to everyone? And meanwhile, I'm going to give you a quick introduction. So Eddie is going to present AllPy, an active automata learning library. So Eddie, if you are ready.
Yep, can you see my screen now?
Yes, perfectly.
Okay, so hi. So I already introduced myself, I'm Eddie. And today I will be talking about our library. So we develop a library for active automata learning, as the name suggests. So let's start. So why have we done what we're doing? So a bit of motivation. So why do you need automata learning at all? So let's say you're given a black box system of some kind. It doesn't have to be black box, but it's easier to see it that way. And the only thing you can do with it is to interact with it and observe outputs. So think of some protocols like Bluetooth or MQTT or coffee machine or vending machines are often used examples also. And given that black box system, you would like to perform some verification and testing, and it would be also nice to automatically generate its model. And how to do that? And you can do it with automata learning. So more precisely, active automata learning. That's the variant where you interact with the system. So on very abstract level, you do it by posing 2 types of questions to the system. First is you ask him a question given this test sequence or input sequence, what are the outputs? And based on that, you with time form some theories. You create a hypothesis or a finite state automaton, and you're curious, is that actually what, does that automata correctly describe the underlying behavior of the system you're trying to learn? And that's answered with equivalence query. which either says, yes, that's the same, or no, it's not the same, and here is the counterexample to the equivalence. And then you analyze the counterexample and continue learning. So with that in mind, let's see one practical use cases. So this is from an upcoming paper on formal methods, work of my colleague. So basically, she did the automated modeling of Bluetooth Low Energy system on a chip devices. So as this image suggests, so you're giving this system on a chip, and you would like to generate some kind of a model. So how can you do that? And a missing piece in the puzzle was ALPI, basically, so our library. Of course, there's other library for packet manipulation, but the actual learning is done with our library. So some general info about it. So why have we done it? So we realized that there is no standardized automata learning library in Python. The most notable one that there exists is LearnLib, and that's in Java, which is a very good library, but we have different focuses to it. So also ALPI, we claim, at least in so far, it has been proven to be easy to extend, experiment with, and use. And we use it at least, and we hope that others will use it as a hub for further research in the domain of active automata learning. So on more technical note, it's written in pure Python with a single dependency for visualization of automata, and you can install it with one line, which is always useful. A big effort was put on a documentation, a lot of usage examples and wiki. Yeah, mostly usage examples, because even though we have documentation and Wikipedia wiki site for it, nobody likes to read that, and everybody just wants to see how it works. And it's hosted on GitHub, links in here. So how do you actually learn some system with ALPI? So we formulate it as a three-step process, so to say. First, you have to implement the SAL interface, or system under learning interface, which basically says, okay, I want to learn this. So if you want to learn some Bluetooth protocol, you need to implement methods to interact with it. And given this abstract input, execute this abstract method. So once you've done with that, and you know you implemented this wrapper around the thing which you want to learn, then you have to choose one of the existing or implement your own and provide parameters for an equivalence oracle. That's that part which will answer, is the current hypothesis correct or the same as system under learning. And once you have done that, you just need to run the learning algorithm. So you just call it, provide few parameters and optimizations if you want, but that's it. If everything works, hopefully you will get a model out of it. So looking at the code here, let's imagine that we have some system that behaves as a regular expression. So we can define the regular expression, but to the learner is completely black box. So it can just interact by posing queries with the input alphabet, with just knowing input alphabet. So we create this instance of this system under learning interface with some regex. On the next slide, we will see what this is. We choose an equivalence oracle. We call the learning algorithm. So simply run L star with the input alphabet system under learning equivalence oracle. Currently, we're interested in DFA, and we get learning statistic out of it as the learning goes. And we can also visualize the automata, for example. So that would be a simple example, but most of the learning setups follow this three-step process. So how do you actually implement this SAL interface, which is the most important part when you're trying to learn some system? So all systems are learned by interacting with them, as I said. So, and to do so, you need to be able to query a system and to perform a reset on a system. A query is implemented as a sequence of individual steps on a system. So you only need to implement a single step and the query is implemented in the backend. Of course, you can implement custom queries, but most likely you won't need it. And the reset, we just need to reset so that every time we pose a new query, we start from the initial state of the system under learning. So therefore, we have three methods for that. One is step, which is obvious. We execute an input and observe an output. In the step, you would also do abstraction. Basically, you provide some, in many cases, like learning protocols, you would provide abstract input, execute concrete input, observe concrete output, and return abstract output. And pre and post are just the reset, but split in two parts. So pre is executed before query, which is initialization part, and post is like for graceful shutdown and cleanup. So to test for regular expression, we only need to keep a track of one test string, so to call it, and add the current input to it. And then a query will just be, is this word in a language or not? This is the simplest example, but I hope it demonstrates the point. So equivalence oracles, as I said, they try to falsify the current hypothesis, and we do that with conformance testing. Equivalence checking is undecidable in nature, but yeah, there's also, but you can simply provide some guarantees also with random sampling, like probably approximately correct oracles. Or you may do exhaustive testing and hope that all counterexamples are found. So we provide 10 different equivalence oracle in AlpI, from W method, which is one of the most famous ones, but it does not scale to large systems, to many different completely random ones, and some that exploit the structure of the learned hypotheses, which are usually the best. And to add new equivalence oracle, which is also an interesting area of research, is very easy. So you just need to implement one abstract class, and we support the designer by providing path to the shortest path to each state in the automaton, and the characterization set of the automaton and stuff like that. So now when we have the system under learning class implemented and equivalence oracle selected, let's see what we can actually learn. So we can learn deterministic system, non-deterministic system, and stochastic systems. So one thing to note is the learning process or learning setup stays the same. To just change the type of the system from deterministic to non-deterministic or stochastic, you just need to invoke different methods. But this three-step process remains the same. You just change the last step. So you don't think call run L star, you call run stochastic L star, for example. So this table summarizes everything, so to say, but we're going to explain it in the next few slides. So for deterministic systems, we support standard DFAs and final stage transducers, more concretely Mealy and Moore machines. So that is standard L star presented by Algluin. We also have its variants, which are Rivers-Shapiro or Shabazz-Gross. Basically, those variants are called after the counterexample processing strategies, which are quite important and reduce the runtime substantially. So, and one important thing that we implement seamlessly for the user, because user is not even aware of it and doesn't have to do anything for it, is caching. Basically, if a query does not need to be asked, so if a test case does not need to be executed because we have already seen its prefix, because it is a prefix of some other test case that was executed in past or during equivalent checking, caching will be invoked and a lot of time saved. So caching is really important, especially on non-simulated systems. Of course, caching invokes that we can simply check for cases of non-determinism, which is quite useful because if you're trying to learn deterministic system, there should be no non-determinism. And we also implement various smaller optimizations to make it as efficient as possible. So non-deterministic systems. So we support observable non-deterministic finite state machines and abstracted non-deterministic finite state machines. So observable non-deterministic finite state machines are basically, you can look at them as non-deterministic Mealy machines, but you always have input-output pairs are distinguishable. So one input can have multiple outputs, but one input cannot have many more outputs of the same type. So these algorithms rely, as they're presented in their original implementations, on an all-weather assumptions, which basically mean if I query a certain test case n times, I will observe all possible outputs which this test case can produce, hence the non-determinism. But this is quite a strong assumption to have. So currently we're developing an algorithm to remove this limitation. And this algorithm is mostly inspired by our work on learning of stochastic systems. So here we support learning of Markov decision processes and stochastic Mealy machines, active learning of those formalism, and Markov chains. So L-star MDP and L-star SMM are there for active learning. And we also have a bit of passive learning, but it's still active learning library. So we implemented Allergia. It's a very popular algorithm in the community for generation passive learning of probabilistic models, so Markov chains or MDPs. And we implemented it for personal needs and also, of course, for the community. So it's not only active, also we have Allergia, but that's not the biggest focus there. So these algorithms are not so well known. They're quite recent. This one was just accepted, but they are, you can find more details in the paper if you're interested. So some additional features which make everything more polished is that if you're developing algorithms or counter-example processing techniques or equivalence oracle, you would like to test your approaches. So with support for all formalism, you can generate random automata of any size and various properties. And of course, you can save and load everything from file using the same syntax, more or less, that LearnIb uses and Automata Wiki presents. Everything can be visualized, of course. Learning progress and statistics are printed to various extents, so you can control the level. You may use it to teach students how automata learning works by printing the equivalence oracle, or you may print the basics. And as I said, during learning, we store this information to aid the user in the development of equivalence oracle. And for stochastic stuff, we added the translation of MDPs to a Prism format, because it's quite nice if you can actually model check to see if you're developing algorithms. That's only useful because there you have a controlled environment and you know the value of some properties to model check your learned models to see how well your algorithm works. So one thing about when somebody thinks about active automata learning, so what are the bottlenecks there? How applicable is it in practice, you may think? So real bottlenecks of active automata learning are size of input alphabet, then conformance testing, so the equivalence oracle part, and interaction with system under learning. And the biggest bottleneck by far is interaction with the system, but let's go over the images and then I'll explain. So basically, we can see here that the learning with the constant size of the input alphabet, as the automaton size increases even to 5,000 states, learning is very fast, less than a second, less than a half a second, or in case of DFAs, second and almost 2 seconds. But here we can see this is for simulated environments. Of course, it's very fast and little to no overhead. And as the alphabet size increases and the size of the automaton remain constant, we can see that time also increases quite faster than in the other case. But one note here, so the most costly part of learning is interaction with the system under learning, because when you think about it, when you're learning, let's say Bluetooth, every query that you execute will take half a second, let's say. That's quite a conservative estimate. And then if you execute 10,000 queries, you're already looking at an hour of learning, and they're just interacting with the system. So that's one thing to note. So we're always trying to minimize the total number of interaction with the system. And that's why that caching that I mentioned previously is very useful, because it will save you as much time as possible. So also we can see that these are experiments for our stochastic learning benchmarks. We compared ALPA's implementation with the original implementation presented in Java. And we can see that sometimes one performs better, sometimes the other, but this is due to the minor implementation differences. This is just to show that even though the Python is a slower language than Java, the learning algorithms themselves don't pose too much of a bottleneck. Just interaction with the system is the real culprit. Okay, so there will several case studies, so to call them, conducted already with ALPI. One very nice one, which I will show you the example, was how some researchers found bug in Vim and NeoVim. The other is the fingerprinting of Bluetooth Low Energy, which was done by my colleague, which I presented at the beginning. So then we had extraction of finite state models from the recurrent neural networks trained on regular languages. Here, the ALPI was useful in two cases, because to generate the training data and to perform the extraction. This is done to see how the recurrent neural networks learn internally, for example, and also connecting model-based diagnosis with automata learning. So before I go to the bugs found section in Vim, let's conclude. So ALPA is an easy to use active automata learning library, and we offer a wide selection of supportive formalism and algorithms, and hopefully it will be ever expanding in the future. What's very important is the supports rapid development and prototyping, both for the users of the library and for the users who develop something in the library. And everything regarding ALPI, its source code, its documentation, examples, and wiki are on our GitHub repo. So let me just quickly show you how everything looks like. Of course, leave a star, a little bit of shameless begging never killed anybody, but it helps a reach. So this is our front page of the GitHub repository. And here we see our README. But if you go to wiki, then you will actually reach our wiki, which has many tutorials on what automata learning is, and we actually plan to use it as educational material once it gets a bit more polished with our students. So how everything works in much detail, and also some advanced usages like learning-based testing, learning-based fuzzing, and so on. So this is more for newcomers to the field or somebody who is interested in how to use ALPI. Furthermore, we have quite an extensive documentation for each class in the library. So everything is well documented and can be found in code or online, as you can see here. And also online, we provide several of those so-called interactive examples, which you can open with some tools and then change everything online without the need of installing. As you can see here, this is the standard example often used in automata learning to demonstrate as a baseline. So Angluin's example for her seminal paper. And here, this is the most verbose mode for educational purposes, most often, or debugging, where you can see the observation table as the learning progresses. And also here we have how the learning is set up and how it looks for stochastic systems. So we see here that here observation table has frequencies of outputs and so on. So that would be that from my side. Yeah, let me just, before I go, show you how some researchers use ALPI to find bugs in Vim and NeoVim. So basically, I don't use Vim, so maybe I'm a bit off with the description. You know those modes which you can type in, so insert, exit, command line editing, and so on. So they were curious what kind of a state model do they form. So they basically did this three-step process. First, they implemented the system under learning, where they just mapped the inputs. I hope you can see it. So where they mapped that modes and executed them. So once one input is given, it's executed on Vim, and output is observed. And they managed to generate quite big models of several hundred states, as we can see here. And how did they find the bugs, you may ask? So they did not do any conformance checking against a specification or anything. They just encounter cases of non-determinism when learning. And you would expect Vim to be deterministic, but it wasn't. So they isolated those cases of non-determinism, which they obtained during the learning, then analyze them a little bit, and basically they're already test cases. You can maybe just prune them a little bit and submit it to the Vim developers, and the bug was fixed. So that was nice to see that people used ALPI for such big projects and found some bugs. So thank you for your attention, and happy to hear your questions.
Thank you, Eddie. So any questions from the audience? Please feel free to unmute yourself to ask questions, or you can just type it in the chat. I will ask for you. So maybe people need some time to prepare. I will start then, if you don't mind. So Eddie, I'm quite interested in the conformance testing. So for that part, how do you take use? It may be covered by L-star algorithm, but how do you take use of the counter example to fix the learning process?
Yeah, so that's basically covered by the learning algorithms itself. Basically, the best method to do so is called Rivers-Shapiro counterexample processing. And basically, then you first analyze the counterexample a bit to find the minimal suffix, which caused this distinction between what you observed at your hypothesis and the actual system under learning. So you isolate, so to say, a minimal sequence which distinguishes it. And then you add this sequence to the suffixes in the observation table. So basically you extend this observation table, and then you will have to query some more. It's an iterative process. And with time, these differences will be revealed, and some state splitting will surely occur. So you will get at least one new state, and learning will proceed again to this next learning round. Then you go to the equivalence checking again, and everything repeats.
Yeah, thanks, Eddie. Other questions? If still silence, I'm gonna ask the second question. So Eddie, also for the application to the IoT protocols, so I saw you apply it to Bluetooth low energy and also MQTT. And recently I have a student who is doing the fuzzing to the IoT protocol implementations. So he also covered MQTT and COPE, such kind of algorithms. And I think he also used the automata learner, and I think he's used one called LearnLab. I'm not sure they've heard of it.
LearnLab, yes, exactly.
Yeah, it's implemented in Java, right?
Yes.
So if you can maybe briefly introduce, the difference between AirPi and state-of-the-art learner, and also if you can give more details on the application to the IoT protocols.
Okay, so first regarding fuzzing, we did some recent work also with Learnlib before we developed Alpi on the, we called it learning-based fuzzing. It's basically fuzzing where you are aware of the states of the system, so you can do stateful fuzzing. So you first do the learning to get the model, and then use that model to fuzz the system. No, you use model to generate, to go from state to state and then fuzz. So that's a nice application. So we actually support that, of course, with Alpi. So there's a section about that on Wiki, not too detailed one. So comparison with Learnlib. Learnlib is a very, very nice library. But in, I mean, personal experience is that it's a bit harder to set up and to use. It also supports some formalisms that we don't support, but then again, we support formalisms that they do not support. So neither Learnlib or Alpi supports everything, but yeah, so they're really good, but they suffer from the Java's downsides, so to say. Also, they benefit from their Java's benefits, but setting up an experiment in Learnlib was trickier, and we hope that for other people with Alpi it will be simpler and faster.
Thanks, Adi. Questions, please. Okay, so if no question, let's thank Adi again. I know it's very early morning in your side, so take care and thank you everyone.
Good night, ciao.
Now, yeah, thanks Adi. I'm gonna now introduce the second paper. Is the presenter here?
So I'm going to speak for the second paper. So
Yeah,
I'm Rajarshi. Yes.
Thanks, Rajarshi. So the second paper, Rajarshi, could you share your slides to everyone?
Yes, I could just share my screen.
So meanwhile, let me introduce you the second paper, learning linear temporal properties from noisy data, max set based approach. So Rajarshi, please start if you're ready.
Thank you for the introduction. So hello, everyone. I am Rajarshi Roy from the Max Planck Institute for Software Systems. So I'm based in Kaiserslautern, Germany. And today I'm going to talk about how one can explain complex systems using linear temporal logic, even when the data we have may be noisy. So this is a joint work with Jorafel, Daniel, who is my advisor, Ufuk, and Jay. So let me start. So nowadays, the systems being used in artificial intelligence are becoming increasingly complex. Now, understanding the functioning of such complex systems by humans is a rather challenging task. Now, in order to assist humans to understand complex systems, we aim at learning human interpretable descriptions of systems by observing the behavior of such systems. Now, to make it more concrete, let me show you how we provide descriptions in an example. So let us consider this robot, which is following a complex set of trajectories. Now, the image here describes one such trajectory of the robot. Now, to provide simple descriptions of this system, we consider a setting in which we observe several trajectories of the robot. The trajectories are given as an input sample consisting of a set of positive examples that depict the desirable behavior of the robot and negative examples that depict the undesirable behavior. Now, based on these trajectories, we like to infer a simple description of the system. So for this example, a description which says that the robot is initially in position A and finally reaches position B is one that is consistent with the sample. So in particular, it satisfies the positive trajectories and does not satisfy the negative ones. Now, the description you see here is in a formalism known as linear temporal logic, or LTL in short. And in this work, we are going to use LTL for providing descriptions of complex systems. So as many of you might know, in the recent years, LTL has gained popularity as an explainable model because of two main reasons. So first, it is a human interpretable formalism since it can be translated to natural language easily. Second, it can express temporal properties of AI systems using several temporal operators such as next, until, globally, finally, so on. Such operators allow us to concisely describe properties in various AI domains. An example from robot motion planning domain is that whenever a request is made to the robot, it should eventually be granted, which can be expressed using a formula which looks like this. Now, in this talk, I would visualize LTL formulas using their syntax tree representation because it's easier to view as syntax trees. Now, in the area of explainable AI, this problem of learning LTL formulas is now being looked at extensively. However, this problem is a challenging one since the search space for LTL formulas is in fact infinite. So what people do is, in order to reduce the search space, most of the existing work would rely on user-defined templates for the prospective formulas. So they would use templates which are essentially incomplete LTL formulas whose syntax trees have missing entries. So many of these approaches will fill out the entries with simple LTL formulas using usually propositional variables using variety of enumeration techniques. So while this makes the search easier, the main issue with these approaches is that the user would usually need to provide the templates, and this requires the user to have prior knowledge about the underlying system. Now, there are certain works that overcome this issue. So these works learn formulas of arbitrary structure by performing a systematic search over all LTL formulas. So these approaches, however, are known to be not robust to noise in the data. So in particular, they will tend to produce complex formulas in an attempt to overfit to the noisy data. So contrary to the existing works, our approach can infer arbitrary formulas and at the same time is robust to noise in the data. So to achieve this, we solve the following inference problem. So we are given with a sample consisting of a set of positive and negative system traces or trajectories as I described them earlier, and a threshold kappa. And we would like to infer an LTL formula such that the loss of the LTL formula with respect to the sample is less than the threshold kappa. Now, what exactly is this loss? So here, loss refers to the fraction of traces in the sample which the inferred LTL formula misclassified, right? Now, our problem formulation offers two sorts of advantages. So the first advantage is basically the bounded misclassification that we allow in the problem ensures that the inferred LTL formulas do not overfit the data. Second, the minimality criteria in the problem ensures that we obtain concise formulas, which ensures that the formulas are in fact human understandable. Now, to solve this problem, we propose two algorithms. The first one is a MaxSat based learning algorithm that infers minimal LTL formulas from the given data. The second one is a decision tree learning algorithm that uses the MaxSat based algorithm as a subroutine. So in this algorithm, we trade off minimality of the formula to obtain faster termination. Now we have implemented both our algorithms in a publicly available tool, and we have observed that we can successfully infer small formulas from even samples which are noisy. So in the next part of the talk, I will describe both of the algorithms in greater detail, and I will start with the first algorithm, which is our MaxSat based algorithm. So our first algorithm, essentially what it does is in the crux of it is to encode the inference problem as a propositional formula phi Sn. Now, intuitively, this formula phi Sn enables us to check whether there exists an appropriate LTL formula of size n, that is an LTL formula that has loss less than the given threshold. Now, let me mention here that we define the size of an LTL formula in terms of its syntax tag. So a syntax tag is nothing but a syntax tree of an LTL formula in which the common nodes are merged. So for instance, the size of the LTL formula here is 6 because the syntax tag of this LTL formula has 6 nodes, as you can see here. Now, the propositional formula phi Sn helps us to search for the minimal LTL formula, that is the smallest LTL formula that has loss less than kappa. Now, roughly speaking, our algorithm would iterate over propositional formulas of increasing values of n to search for the appropriate LTL formula. So to understand this algorithm in a bit more detail, we need to understand how this propositional formula looks internally. So let me describe that. So internally, this formula phi Sn consists of two types of constraints. The first type of constraints are called hard constraints, and one necessarily needs to satisfy all of them. And the second type of constraints are soft constraints, and one needs to maximize the number of such constraints that can be satisfied. Right. Now, the hard constraints in the case of phi Sn includes constraints that ensure that the prospective LTL formula has a valid structure, and the LTL formula has a size n. Further, there are constraints that ensure that the prospective LTL formula is evaluated on the traces based on the appropriate semantics of LTL. Now, the soft constraints include constraints that ensure that the prospective LTL formula satisfies the positive traces and does not satisfy the negative traces. Now, it is because of these constraints that the prospective LTL formula are allowed to misclassify certain traces, because these are soft constraints. Now, let me describe an important property of this propositional formula. So the propositional formula we constructed satisfies the property that from an assignment of phi Sn that satisfies all hard constraints, we can extract an LTL formula that has a size n, and the loss of this LTL formula with respect to the sample is equal to 1 minus the number of soft constraints satisfied in the formula. Okay, so now what we would do is basically we would describe how we exploit this formula to devise an algorithm to solve the inference problem. So we basically start with n equals 0, and we iterate over all integer values of n in an increasing order. So for each value of n, we create a formula phi Sn, and we would use an off-the-shelf MaxSat solver to find an assignment to phi Sn that satisfies all the hard constraints and maximizes the number of soft constraints that can be satisfied. Now, in this, we halt this algorithm when we find an assignment in which the number of soft constraints satisfied is actually greater than 1 minus a kappa, which in fact means that the loss of the formula is less than kappa. Now, so what are the guarantees of the algorithm? So first, the algorithm is, so first in this algorithm, this algorithm always finds a Milliman LTL formula that has loss less than the threshold kappa. The minimality is due to the fact that we increase the size of the LTL formula that we are searching for by 1 each time. So it would in fact find the minimal formula. And the loss is less than kappa because of the fact that I described earlier. So loss is equal to 1 minus a number of soft constraints satisfied, and this is less than kappa when the algorithm terminates. The second guarantee of the algorithm is that the algorithm would always terminate. And this guarantee is due to the fact that there is always an LTL formula that has loss equal to 0 on any given sample. I should mention here that the set of positive traces and the set of negative traces are disjoint in this sample. So which is why this holds. Now, this LTL formula, which achieves a loss of 0 on a sample, is usually a prohibitively large formula and generally never a solution to the inference problem. So this is just for a termination. So I should mention here that there is one demerit of this algorithm. So the time required to find assignment to phi SN increases exponentially with the increase in the size n, and which is why we introduce our second algorithm. And so here ideally we would like to use our maxset algorithm to extract LTL formulas with small sizes and exploit them to find a suitable formula, and this is what we do exactly in this algorithm. So we combine small LTL formulas that we obtain using maxset algorithm to form a decision tree over LTL formulas. So what is a decision tree over LTL formulas? It is nothing but a decision tree in which the decision nodes are essentially LTL formulas that you can see in the picture. So one can even construct an equivalent LTL formula from a decision tree over LTL formulas. Now, this algorithm is essentially a standard decision tree learning algorithm, and so these are the most important steps in the algorithm. So the algorithm takes as input the sample, the threshold kappa, and additionally it takes as input an user-defined parameter mu, whose significance I will explain in a moment. So the first step is in this algorithm is to infer a concise LTL formula for a decision node of the tree. And after we do so, we split the sample based on this formula. And then what we do is we check the stopping criterion on the resulting samples. If they do not hold, then we recursively apply the decision tree learning algorithm on the resulting samples. Now, while these are the standard steps in the decision tree learning algorithm, the most interesting step in this algorithm is to obtain the LTL formulas for the decision node. So here, the goal is to search for formulas that have a small size. These formulas, this formula need not classify the sample perfectly well. So a solution is to use a maxset based approach to find a formula with a good score on the sample. An example of a formula with good score can be one that has loss less than mu. Here mu is the user defined threshold, which is usually greater than kappa. Now, different score functions have different advantages and disadvantages. Here I will refer the interested audience to our paper for detailed description of the different score functions that we have used for this algorithm. Now I will talk a bit about the guarantees of the algorithm. So in this algorithm, again, we have the correctness guarantee, meaning that we obtain a decision tree over LTL formulas that has loss less than the given threshold. And this is ensured by the stopping criteria that we have for the decision tree learning. Moreover, this algorithm again has the termination guarantee, and the termination guarantee depends on the choice of the score function that we use for inferring formulas for decision nodes. So I should mention that this algorithm, however, does not ensure minimal formulas, but we have observed faster termination while performing experiments. So now I will talk a bit about the experiments that we have conducted. So in the experiments, we wanted to answer what is the performance gain that we have achieved when learning LTL formulas from noisy data. So towards this, we have implemented a prototype of both our algorithms in a Python tool using the MaxSat solver of Z3. So this tool is publicly available in GitHub. Further, to compare the performance of our tool, we have compared it against a state-of-the-art learning tool by Nider and Gavran. So this tool, their algorithm is basically a SAT-based learning algorithm that learns LTL formulas that perfectly classify the sample. And so this algorithm is not known to be robust to noise, and we wanted to see how they compare in noisy data. Now, the benchmarks we use for comparison are synthetic. So they are generated from 12 LTL formulas that are used in practice, and we have obtained them from a study by Dwyer and others. So we generate positive and negative traces from the formulas, and then we add noise to the sample by switching the labels of the traces randomly. So in the experiments, I will show, so I have introduced 5% noise, that is, I have switched the labels for 5% of the data in the samples. Now I will provide just like a glimpse of an experiments. So I demonstrate one comparison in which we compared our MaxSat algorithm to the SAT-based algorithm by Nider and Gavran on this set of benchmarks. So the for the MaxSat algorithm, we have chosen the amount of misclassifications allowed to be 10%. And what we observed is that we have a considerable improvement in running time performance. So this is the running time by Nider, the algorithm by Nider and Gavran. This is the algorithm, the first algorithm, which is the MaxSat based algorithm. And as you can see, the lower half of the chart are the ones in which our algorithm ran faster. So our algorithm, in fact, ran faster in 138 instances out of the total 148 instances that we chose. Moreover, we also compared the size of the formulas that we obtained. So we obtained, we observed that the formulas that we get are always smaller than or equal to the ones that is obtained by Nider and Gavran, as we expected. And again, here, the ones in the lower half are the ones which actually are smaller. And the red ones are the ones that timed out. Now, this says that we are able to recover more formulas, and our formulas are shorter in size. So I would like to conclude by saying that in this work, we devised two novel algorithms for learning formulas robust to noisy data. So we have also established empirically that our algorithms can indeed infer LTL formulas from noisy data. Finally, as future work, we would like to extend our algorithm to our other expressive logics, such as PSL, STL, and so on. Also, we would also like to look at other learning settings, such as a setting in which there are only positive examples, since without negative examples, one can just infer true to be the shortest formula, and that is not helpful in most cases. So thank you for listening, and I'll be happy to take questions.
Yeah, thanks, Rajesh. Questions from the audience? I have one question actually.
There's a question from Jilin. There's a question,
Oh.
Guangdong. There's a question from Jilin.
Yeah, Jilin, please.
Yeah, thank you for your talk. So I'm wondering, actually, can you give some concrete example or applications that this scenario applies? I mean, so maybe some applications there you have noise on the traces, you know.
Yes. So the application mainly comes in a variety of places. So there are examples. So this kind of algorithms are very useful in the area of robot motion planning, where you have like traces of the robot, and you would really like to know how the decisions are being made in the robot, and an LTL formula is very good fit in such cases. So so the noise there could be so errors by the robot sensors that detect there could be errors in detecting some trace, and they might be misclassified, and this could be a case scenario of noise. So there is also this kind of learning algorithms are useful in specification mining, in which you have certain programs or certain systems, and you would really like to understand like what is the source of the bug, and there you can have these kind of scenarios.
But where the noise comes from, if you're in the specification mining?
Yes, in the specification learning, usually there would not be any noise. So if it's being labeled manually, then there could be a noise, because there could be like a mistake by the engineer or whoever is giving the traces. But in general, the specification mining setting does not have a lot of noisy data.
Okay. I mean, somehow it's interesting. It may be more interesting that in the experiments somehow you apply this. You have some examples or benchmarks from the practice, like this robot mining.
No.
Mining,
No, not really. Yes, that is something we are looking forward in the future, having some actual examples from robot motion planning and testing them.
Okay, thanks. Yeah.
Yeah, thanks, Julie. Any other questions and comments? So here I have one question. So Rajesh,
Yes.
if so, the N is the number of clouds, right, or the literal?
Yes.
So what is the scalability if you increase the number of the clauses? The one you have five NS. So the N is the number of clauses, right?
N is the size of the LTL formula, the size of the entire LTL formula.
Okay. So
Yes, go ahead.
Yeah, so my question is, as N grows, what is the scalability of the your algorithm, your learning algorithm? Have you evaluated on that?
Yes. So so we have tested, although it's not there in the paper, we have as future work, we have also tested like how these kind of stat-based algorithms perform when you increase in terms of scalability. So while we have seen that when we increase the sample, that is the number of positive and negative traces, it scales very well. Like it could go up to like 2000 and 3000 and so on number of traces, but that is not the case with the size of the formula. So when these sizes start increasing, so I would say even for a size 10 and 12 and so on formulas of this sort, the SAT-based algorithms start failing, because they have to basically enumerate through all LTL formulas of size 12 to find one, and this is something which is a very large exponential. So
Okay.
this is
Also, it relies on the solver, right? Constraint solver.
it's yeah. So
because to calculate the loss, right, you need to invoke the solver.
Yes, so the more efficient the solver is, the better our algorithm would be.
Yeah. Any other questions? We still have 3 minutes for a quick one. So if not, I'll give maybe the last question. So here you use set. That means you assume the class, all the variables are Boolean variables. So what if you need SMT? I mean, basically, what kind of constraint is it? Why don't you need SMT to specify the system?
So for this, I would say that so a SAT is sufficient for this, because what we are essentially doing is we are essentially so for this part of the so here we are, so the second type of constraints that we have is trying to evaluate whether an LTL formula satisfies the sample, and this is a polynomial time algorithm. So a SAT evaluation is enough for doing so, because we don't really need to go to SMT, because that has more expressive power and we don't require so much. But it is a good, I mean, we could also try that and see how this works, but our guess is maybe it's a slower possibility that's there.
Yeah, but you are right. It depends on the semantics of the system.
Yes.
Right?
Yes.
Okay. Yeah. Thanks. Thank you. I will invite everyone to thank Rajesh again for his presentation. And now I'm gonna introduce the last paper from I think Sarah. Just now, yeah, Sarah.
Hey everyone, I'm Sarah.
Could you share your slides to everyone?
Yes, sure.
Yeah, thanks. So Sarah is gonna present their paper, Mining Interpretable Spatial Temporal Logic Properties for Spatially Distributed System. So Sarah, please start if you're ready.
Yeah, thank you so much for the introduction. I'm going to present my work on mining interpretable spatiotemporal logic properties for spatially distributed systems. This work has been done in collaboration with my advisor, Geothermal Deshmukh from USC, and Laura Nancy from TU Vienna and University of Trieste. What is the motivation behind our work? Spatially distributed systems generate a large volume of spatiotemporal data, and engineers are usually interested in extracting high-level information from such data. In this work, we assume that we don't have access to label data, therefore we are interested in clustering of spatiotemporal data. Examples of spatially distributed systems that generate such data is IoT, complex sensor networks, and multi-agent robots. There are popular techniques in ML community for time series clustering, such as k-means, hierarchical clustering, agglomerative clustering, and shapelets. Those approaches are usually fast, which is the advantage, but they are based on shape similarity. In some applications, it's possible that the traces have dissimilar shape, but they should be clustered in the same group. So such ML approaches are not appropriate for that. And also ML techniques, traditional ML techniques usually lack interpretability. And there are also techniques based on signal temporal logic or STL for learning from time series data. STL is a logic over a Boolean and temporal combination of signal predicates. And there's a considerable interest in learning STL from traces. However, there's limited work that considers spatial aspect of the data. In this work, to the best of our knowledge, we proposed the first set of algorithms for unsupervised learning of spatiotemporal data using formal logics. The agenda for this talk is as follows. First, I'm going to explain the required background. Then I will elaborate on our method. Next, I will present the results. And finally, I will give conclusions. First, we need to model our spatial configuration that we model it as a weighted graph that L denotes the locations and W is the proximity relation between locations. For example, it can be a spatial proximity. Here you see an example, which is a connectivity graph, and we connect those locations that are within distance less than 1 kilometer from each other. And what is a spatiotemporal trace? A trace is a sequence of data values indexed by timestamps, and a spatiotemporal trace associates each location with a set of time series trace. For example, here for location L2, which is green, these are the set of traces that are generated from this location. The same for other locations. And spatiotemporal data clustering is the process of grouping data with similar spatial attributes, temporal attributes, or both. It's possible that two locations that are far from each other are clustered in the same group because of the similarity between temporal attributes. Signal temporal logic, or STL, is a logic over Boolean and temporal combinations of signal predicates, and it's a popular formalism in formals method community to express properties of time series data, and it has many applications such as in biology, robotics, automotive systems, and etc. Here is a trace that is bounded between 1 and 3 for the interval of 0 and 100, and a good STL to describe this trace is always between 0 and 100. Signal is bounded between 1 and 3. And spatiotemporal reach and escape logic, or STREL, is an extension of STL with two spatial operators, reach and escape. Some other operators, such as somewhere, everywhere, and surround, can be derived from reach and escape operators. Here I will explain reach and everywhere operators, and you can refer to these tutorials to know more details and examples about other spatial operators. I will explain the reach operator with an example. Here is the specification or the formula. Yellow reaches green within the path of 1 and 4. And the node L3 satisfies this formula because there is a path from L3 to the green node, which the length is 4, and all the nodes until reaching the green node are yellow. But for example, L4 does not satisfy that because the length of the path is 5. We want the length to be in the interval 1 and 4. Here we assume that the length of each edge is 1 for simplicity, but we can also have like other lengths as well. An everywhere operator, here is an example. Everywhere between 2 and 3, and the node is yellow. And the node L1 satisfies this property because as we see here, for all the nodes that are within distance 2 and 3 from L1 are yellow, and L2 does not satisfy because, for example, node 15 is within distance 2 from L2, but it's not yellow. And parametric STREL or PSTREL is to just replace values in the formula with parameters, such as this formula. What is monotonic PSTRL? We first define the polarity of a parameter P in the PSTRL formula. We say polarity of a parameter is positive if it is easier to satisfy P as we increase the value of P, and it's negative if it is easier to satisfy P as we decrease the value of the parameter. And monotonic PSTRL is a PSTRL formula that all the parameters have either positive or negative polarity. For example, here we see everywhere between 0 and D, the formula phi is satisfied. The polarity of D is a negative, because if everywhere between 0 and D, some property is satisfied, for any D less than that, also the property is true. And what is the validity domain of PSTRL formula? Given a location L and a set of spatiotemporal traces X associated with that location, all the parameter valuations that make the traces X satisfy the STRL formula are valid domain of PSTRL formula. And the boundary of the valid domain is those parameter valuations that make the robustness close to 0 for at least one trace in X. Robustness means the distance to satisfaction or violation. Here is the overall trend of the valid domain boundary for this PSTRL formula. Here are the high-level steps for our approach. First, we need to build a spatial model. Then we project each spatiotemporal trace to a tight parameter valuation in the parameter space of a given PSTRL formula. Then we cluster those projections. We assume those projections as features for our clustering algorithm. Then we need to learn bounding boxes around the cluster, and from those bounding boxes, we learn STRL formulas for each cluster. Finally, we try to improve the interpretability of the learned STRL formulas using decision tree pruning algorithms. And to construct the spatial model, the naive approach is to just make a fully connected graph by connecting every 2 nodes, but this results in a large number of edges and hence it's expensive. A better approach is to just connect nodes that are within distance less than some threshold, and it results in a lower cost, but it creates a disconnected graph which affects accuracy. For example, here 2 nodes are kind of a little bit, their distance is a little bit greater than threshold, but it assumes that the distance between them is infinity because it assumes that they are disconnected. We use minimum spanning tree to preserve the connectivity of graph, but still the problem with MST is that for sum of node, there is a large distance over approximation. As you see here for nodes 1 and 8, the distance through MST is much larger than their direct distance. So we propose an approach to mitigate this distance over approximation. What we do is we first construct the MST, and for each 2 nodes, we compute the shortest path through MST and compare it with the direct distance between nodes. If the shortest path gives a distance greater than alpha times the directed distance, where alpha is 2 here in our experiment, then we just connect the nodes with an edge. Here the graph is still sparse and hence it has a lower cost, but it doesn't have the distance over approximation that MST gives. The second step after building the spatial model is to map each spatiotemporal trace to a tight parameter valuation for a given PSTRL formula. PSTRL formula should be provided by the user based on the domain knowledge. For example, here the PSTRL formula for a bike sharing domain is that always between 0 and 3 hours, somewhere between distance 0 and D, the number of bikes is greater than C. And the tight parameter valuation is not unique, and usually there is a boundary of tight parameter valuations. For example, here, the monotonicity direction of, or the polarity or monotonicity direction of C is negative and D is positive. That's why here is the most permissive point, which results in a highly positive robustness value. And this is the least permissive point, which results in a highly negative robustness value. And the points in the middle are usually associated with points with robustness close to zero that we are interested. But since it's not unique, we use a technique. Actually, we extend a technique that has been used by a previous paper, logical clustering and learning from time series data. And the technique is to that technique is used for STL formulas, and here we use it for STRL formulas. And what it does, it assumes some ordering on the parameters, and it tries to optimize the parameters based on this order. And this order usually is provided by the user based on the domain knowledge. And for example, here, if the ordering first assumes D and C, first we do bisection search on D to find the tight parameter valuations for D and then for C. In this way, we learn a tight parameter valuation for each trace. Now, the next step is to perform a clustering on these tight parameter valuations, and we use agglomerative hierarchical clustering technique to do the clustering. Here is the result of clustering, and a question is what should be the number of clusters. In our case studies, we chose the number of clusters based on domain knowledge, but there are some techniques to find the number of clusters automatically if there is no domain knowledge, using Silute metric, which is a popular metric to do that. After performing clustering, now we need to learn bounding boxes around each cluster so that we can learn STRL formulas from those bounding boxes. To do that, we assume the label of each point as its cluster. Here, the labels are green, red, purple, which are the clusters that each node is associated with. And then we run off-the-shelf decision tree algorithms, and here is the result of decision tree. And I show it in a 2D domain as bounding boxes. These bounding boxes are learned by decision tree. Now we can learn an STRL formula for each bounding box. Here are the formulas associated for with each cluster. Phi green is equal to Phi1 or Phi2, which are the bounding boxes. The same for Phi red, and for purple, we only have one bounding box. And here's the technique to use to find the STRL formula for each bounding box. And a similar work has been done for STRL in the same for STL in the same paper, and we extend it for STRL. And the technique is to consider first to consider the monotonicity direction. Based on the monotonicity direction, we can know the point that results in the most permissive formula, which is here, because the monotonicity direction for D is positive and for C is negative. And then we consider a formula that covers this space and not have two formulas that exclude this space. Here, as you see, it's phi C1, C2, which is the point, this point, and not have phi of C1, D1, which excludes this area, and not have phi of C2, D2, which excludes this area. That's why we are left with this box, and this formula is associated with this box. And we already know what is phi, and we just substitute that, and we get the STRL formula for this bounding box. However, it's possible that we learn like many boxes, many bounding boxes for a cluster, and this will result in a long and hence not interpretable formula. What we do, we use a k-fold class validation algorithm to prune the decision tree. And when we prune the decision tree, we get a fewer number of bounding boxes. However, we get we have to sacrifice accuracy for that. We reached from 5 bounding box to 3 bounding boxes, but the accuracy decreased to 93%. That's the price of getting interpretable formulas. In this way, we can get only one bounding box for each cluster. We use 4 benchmarks to evaluate our approach. The first benchmark is COVID-19 data from LA County. As all of us know, COVID-19 pandemic has extremely affected everyone's lives, and understanding the spread pattern of COVID-19 in different areas of the countries helps to stop the spread of the disease. In this work, we focus on new positive cases in each region of the LA County. And another benchmark that we consider is bike sharing data from the city of Edinburgh. Bike sharing consists of a number of bike stations that are distributed over a geographic area, and we focus on the number of bikes and number of empty slots in each bike stations. And we are interested in analyzing the behavior of each bike station. For example, if there is a bike station that usually runs out of bikes, that's an undesirable station, and maybe the user should avoid going to that station. We also have 2 other benchmarks that I will skip in this talk for brevity, but you can always refer to paper to know more details about the other benchmarks. For COVID-19 data from LA County benchmark, this is the PS trail formula that we consider somewhere between 0 and D. Eventually, in the interval of 0 and 12 seconds, the number of cases goes beyond C. And we fix tau to 10 days because it's easier to visualize 2 parameters here. And it's obvious that if D is small and C is large, those points are hot spots, because it means that within a small radius from the region, there is a large number of new positive cases. And here are the results of projections for the different areas of the LA County. And as we see, these red points have large C's and usually small D's. That's why these red points are hot spots. And these are the bounding boxes that we learned using decision tree algorithms. As you see, we have learned like many bounding boxes for especially these blue and green. And this will result in formulas that are not interpretable. That's why we apply our pruning algorithm to get fewer bounding boxes at the price of lesser accuracy. And finally, we map each point to its region in LA County, and we can see the hottest spots on the map. And this is the formula that we learned for example, for the red bounding boxes or red cluster. And it means that somewhere between distance around 4,000 meters, and within the 10 days, the number of new cases goes beyond 3,181. Or somewhere within a distance which is larger, even the number of cases goes higher. And the next benchmark is bike sharing data from the city of Edinburgh. This is the formula that we consider to analyze the behavior of bike stations. Always between 0 and 12 seconds, either fee wait or fee walk is true. Fee wait means that how much the user has to wait for a bike or empty slot to become available, and fee walk means that in how many far the user should go to find a bike or a slot availability. It's possible that there are some stations that sometimes don't have bike or a slot available, but there's a nearby station that has bike slot availability. Then the user or customer can go to that nearby station, walk there and find a bike and a slot availability. So if we get a small d, which means that there's a nearby station with bike or a slot availability, that's desirable. And here are the fee wait and fee walk. Fee wait means is eventually between 0 and tau number of bikes goes beyond 1, which means there is some bike available and there is some slots available. And fee walk is somewhere between distance D, number of bikes is greater than 1 and number of slots is greater than 1. So locations with large tau have long wait times, and locations with large D are far from stations with bike slots availability. And here are the results of projections. The green points are desirable stations because they have a short wait time and a smaller walking distance. But for example, this is associated with a long wait time, and this is the most undesirable station because it has large D and large tau. And here we just map the points that we learned on the map of the Edinburgh city. As we see for this station that is undesirable, and also this one, these are far from other stations, and maybe that is caused them to be undesirable. Because if they run out of bikes, there is no nearby stations. And here is the formula that we learn. And the first part of the formula is negation of a short wait time. And the second part is also meaning that negation of a short walking distance, which means that the red stations have long wait time and large walking distance. Here are the summary of the results, and as we see, L denotes the number of locations and W is the number of edges in the spatial model that we build. As you see, and there is a kind of direct connection between the number of edges and runtime. That's why we prefer to have fewer edges in the spatial model. These are the number of clusters, and this is the length of the formula that we learned for each cluster. And as you see, the formulas are quite short and hence interpretable. To summarize, we have proposed a technique to learn interpretable STRL formulas from spatiotemporal data. We proposed a new method for creating a spatial model that restricts the number of edges, at the same time preserves the connectivity of the spatial model. And we used a robustness of STRL formulas combined with binary search to extract features for spatiotemporal data clustering. And then we applied agglomerative hierarchical clustering on the projections and combined with a decision tree algorithm to learn interpretable STRL formulas for each cluster of data. And the results that we got show that our method performs slower than ML approaches, but it's more interpretable. The part about comparison with ML approaches is also provided in the paper. You can refer there. Thank you so much for your attention.
Yeah, thank you, Sarah, for the great talk. Questions, please. So just a very quick one, Sarah. In the COVID case, the learned formula, does it really confirm the real world scenario about the spreading, you know, those distribution of the hotspots?
What was the question?
Yeah, so you learn those parameters, right? Do the parameters confirm the real world cases, real world scenarios?
Yeah, exactly. We got this this COVID-19 data from LA County is from real scenarios, and actually we compared this final result that we got, and it was interesting that the hot spot, there was a really good degree of matching between the hot spots that we got and those that were reported by LA County.
I see. Yeah, thanks. Thanks, Sarah. Questions, please. Yeah, so I saw, yeah, Zhiling.
Yeah, thank you for a nice talk. So I'm wondering, I mean, for the formulas, so whether you have some templates where you also learn these formulas,
Yes.
mean, these boundary formulas.
In this, you mean why we have templates?
Yeah, no. I mean, these templates are from somehow some experts, maybe some domain experts, design these templates. These templates, where you learned also you learned these templates from the data.
Yeah. These templates should be provided either by experts or, probably future work will be just to get these templates automatically. And for this work, we assume that these templates are provided by the experts and based on the domain knowledge. For example, for these domains, it's obvious what should be the good templates, but it's possible that for some applications, it's not obvious what is the best template. And for those scenarios, we were going to expand this technique to mine the template automatically.
Okay, thank you. Yeah.
Thank you, Zhilin. Any other questions? So if no problem, I'm gonna transfer to Vijay and Zhe. So thank you for attending this session. Thank all the speakers. Vijay?
Yep.
Yeah,
Thank you, Guangdong. This was really very nice. I think now we can go to the next session. Let me just.
Yeah, so basically the morning session is finished, and we will
we're gonna have a long break.
We're gonna have an
break.
hour and a half, or actually, it's quite a long break.
Yeah, very long break. So the next session would start at 3:30 Brisbane time.
Okay.
3:30 Brisbane time.
All right. Thank you, everybody.
Yeah. Next
See you
chair
then.
is
Bye-bye.
yeah, sure. Yeah. So see you in the afternoon.
Okay, I'm going to.
Always a closer sound.
It's 10 o'clock.